as I said, so we probably need another half hour, like 20 minutes, half hour to finish the lecture from this morning. And what I talk to you a little bit is about if I have a very, very complicated system, or I have a modern system which has graphics cards, accelerators, how would I program these? Yeah, would I use MPI, OpenMP, or whatever? Yeah. Okay. Of course, you have to use yet another thing. Yeah. And there's different ways. Like when you do between nodes, it's basically everyone is using MPI. Yeah, there's always someone who has used something special. If you're going inside a node, almost everyone is using OpenMP. Accelerator is out there for at least 10 years. Different vendors have their own idea how you should program their GPUs. And so currently there was now outcry by all the users who say, yeah, we want one thing. I don't want to learn thousands of different things. It looks like currently everyone is happy to learn the one thing or the other thing, or yeah, it's. But I think at some point there will be a pressure that we only have one standard way to program GPUs. Currently, it looks like it's not hard enough. So I tell you like some simple ways, portable ways, and then some specific ones. So one of the things is basically people liked the idea of OpenMP. You don't do very special. Basically, you don't say how to do this and this and this. You just say make this parallel. Yeah, split up the loop and something. And I thought this is useful, and I want to have the same thing for GPUs. So what they did is people sat together and producing a standard very much like OpenMP. It's called OpenACC for Accelerator. And it gives you directives and pragmas, which you can tell, like run this code on the GPU. Yeah, split up the loop onto the different processes of a GPU. Yeah, it works with very much the same way. There is not many compilers here. There was one compiler which was bought by NVIDIA, and then it works for NVIDIA GPUs. Meanwhile, with the help of OpenMP, with the labs in US, they also have the GCC, starting with GCC 9. OpenACC is also understood for NVIDIA graphics cards by GCC, and with version 10, it also understands AMD. So if you want to use either AMD or NVIDIA cards, and you have a very new and latest open GCC, GNU compiler, then you can use OpenACC. But better even, in the latest versions of OpenMP, starting with 4.4, it was probably not usable, but 4.5 or 5. So if your compiler, and you have to look in the documentation, is supporting OpenMP 4.5 or later, there's also OpenMP extensions and pragmas who can also program on a GPU. Yeah? So basically this is directive pragmas. The other way is, but this typically only works for C++ because all modern codes are typically written in C++, high performance codes. There is different libraries. There's Cocos from Lawrence, from Los Alamos, Raja from Livermore, Alpaca from some German universities. There's 10 different things, kind of like dialects or libraries in C++, which on a very high level you can specify that. Yeah, and then like here, basically, you wanna add two vectors, and you multiply the first vector by a constant and then adding a second vector, and you want to do that in a normal, you would say 4 from I to n, and then with either OpenMP or MPI make it in parallel, and now you basically say, oh, in C++ this is a Cocos parallel 4, and then basically it creates the special code automatically for you on the GPU. Yeah, the same thing up here for OpenOCC and target. So I have an example. So if I want to run my value of a polynomial program, yeah, but you have to have an OpenMP with version 4.5 later. So the blue part is the OpenMP version. And now I don't want to run on my CPU, but the target, I want to go target somewhere else, which is I want to basically go to an accelerator, yeah, and then I want to use, I can't explain it easily, but basically I want to use all the facilities of graphics cards. I want to distribute it on different teams, and then do this parallel 4 reduction onto the GPU. Yeah, so it means take the parallel 4 and reduce it, put it on the target, and there distribute it to the teams on the GPU. And then that code, you have to probably specify with an environment variable or by a compiler flag. Should it generate code for AMD or NVIDIA or something? But then it does it for you. So like if you're happy with these simple things, you can do it. You typically have to add a little bit more. And the problem is with this private and shared. So what stuff? You have to get the data into the GPU and get out of it. And this is costly, yeah, because if you have huge vectors, it takes a lot of time to copy the data into the accelerator, or when you're done, copy it out. So by default, only like an integer or double, like single values are copied in and out. If you want to copy other stuff in and out, you have to say, yeah, like here we need the coefficients to run it. So we say, we map the coefficients into the accelerator and in. And if you want to have it out, you say map out from, and then it copies it out, or to and from. But basically, again, it's just one line, and you can program GPU in a simple way. And this is basically OpenACC, where the compiler, because it has more knowledge about the GPU and anything, so you don't even have to specify these teams things and in and out stuff. Meanwhile, I mean, for a long time this was the only way of doing it with directives. Meanwhile, meanwhile there is an OpenMP version, which is like more standard, and meanwhile there's more and more compilers doing a good job of doing it. I would personally recommend to try OpenMP target. Okay, and as you see, and Fortran again, it's basically the same thing. Okay, the advantage if you're doing it this way, yeah, it's basically like OpenMP. Yeah, you have the same version, whether it's sequential, OpenMP, or accelerators. You just recompile and you get a different version. You don't have to have separate programs which you have to maintain. You can do it incrementally by adding directives by loop. Yeah, if you just have one large loop you want to put on the accelerator, you just add one pragma, and then if it's still not fast enough, you look at the second largest loop, and so on. And what basically it does, it makes sure all the necessary data allocations and moving the data from the CPU onto the GPU, and the data after you're done out. Reductions, and also you have to kind of think, because again, the GPU has like I showed you yesterday, has multiple thread blocks, and each thread block has number of thread units. You don't have to think about, how should I map this on the different execution units on the GPU. This is all done by the compiler. And you can use your normal build scripts or so. Yeah, you have a make file or something like that where you say compile blah, 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 and here's the same thing. Yeah, it's just compile with different options. If you don't, if you basically say, oh, I want to really, like in MPI, I want to make sure myself, when is stuff copied? When is things reduced? I want to specify the block sizes. You can do that. Yeah, but basically all of that, then you have to do yourself. And you have to know how to do it and how to do it efficiently. Okay. So this is where low-level GPU programming comes in. And the thing is, now, this is basically provided by the people making the graphics cards. Yeah, everyone has heard of CUDA. So CUDA is basically, if you want to say, I want to use NVIDIA graphics cards, I want to use NVIDIA software, but CUDA only works for C, C++. If you have Fortran, I think there's also meanwhile stuff for Python and things like that, but Fortran is typically not so well supported. Then AMD came later, and they introduced something like HIP. The fun thing is, they were intelligent enough not to do it totally different. Basically, what they did, they took the CUDA documentation, and every time there is like the word CUDA, they replaced it by the word HIP. So instead of calling the function CUDA-malloc, you have to now to call HIP-malloc. So it's basically the same thing. There's a few small differences because AMD GPUs are different. So you have to have different versions of a code, but both of them are very similar. And there are typically little utilities where you can automatically translate CUDA into HIP code and HIP code into CUDA code. But it's basically like MPI. You take your code, and then you have to all these functions, allocate the data here, transfer it now to the GPU, do this, create this kernels, and blah, blah, blah. It's kind of complicated. And then there's a portable way, OpenCL, which is more C, or even better, there's a C based on C++, there's SYCL, which is a different way of thinking, but this way allows you also to specify at very low level, but you can run it now on a GPU, on a CPU, it runs on all kinds of devices. It's low-level accelerator programming, but independent of the devices, but still low-level. Okay, the thing is, you can combine it. Yeah, so you start with, say, OpenMP target to make your program work on the GPU, but then there's this one important, like the center of your program. Yeah, it's like typically one large function which gets called over and over and over because you have these iterative solvers or something, and it's not running, the compiler doesn't do a good job automatically generating accelerator code. Then you basically just that function you write in CUDA or HIP yourself. Yeah, and the simple parts which just work solely, you use OpenEP target or OpenACC, and you can combine it. Yeah, so you basically, yeah, like as I said, start with OpenACC or OpenTarget, and then for things who don't work very well, or you think you know better than the compiler, then just these parts you write in CUDA and on HIP, and you can combine these things. Yeah, and here's some examples. Because, as I said, a GPU has these kind of blocks of threads, thread processors, and then each of the blocks has a number of simple thread processors who work in a synchronized way. You have to structure your things in blocks and kernels and so on. I don't want to go in details. We cannot do it here on Fukaku anyhow. And I have to admit, I'm not a big GPU expert, so I cannot really explain it nicely. You have to ask a younger person. Okay, yeah. And here's kind of like, if you want to do a simple thing, yeah, like I have, this is a typical functions in linear algebra, yeah, so I have that I want to take a vector, multiply it by a constant, and add another vector. This is called Saxby. Yeah, you would write it basically in this way, If you want to do it in parallel, this is how you have to rewrite it. Yeah, you add global in front of it, and then you basically, yeah, like you say, okay, all these processes on the thread, I want to use them because I just have a vector in a one-dimensional way. Basically, you have to write the code which is executing for one index, like for one value of I. And then you have to basically calculate here, yeah, inside my block, basically, where is that the thread processor and execute it. And then because in some cases, like the vector length is not matching the number of thread processors, you have to be careful that only if you are smaller than the number of vectors this is executed. So if you have more thread processors there, that they don't try to access vector elements which don't exist. And then basically the same thing here is in HIP, and on that level is actually the same, but you have to include HIP runtime, and here you don't have anything. But this is just basically this one kernel. Oops, sorry. Okay, yeah. But then, yeah, this is you have to write a main program to actually call that SEXP operation. So first you have to allocate the data to make it sure, and then this only works if you have a modern GPU who basically can use the memory together with the CPU. If you have an older version, you even have additional calls to copy the data from your CPU onto the memory of a GPU with a CUDA copy. Then you initialize it, and then basically you set up these block sizes, and then you call your SEXP operation on that block sizes, and this is actually then the call onto the GPU. And when you do synchronize and free the stuff, yeah. So you see, just for this little example, to like adding a constant or multiplying a thing and adding a vector, you have to write a lot of code. And now imagine if you have like a real calculation, how you have to write CUDA code. So this is why I start with OpenMP target or OpenACC, where you just add some pragmas. It's typically fine, yeah, unless you are. Yeah, like someone says, oh, yeah, you have to use Fukaku or whatever, or a large NVIDIA cluster, and it's so expensive, and it has to run much quicker. Yeah, don't do the pain. Yeah? It's only if it's necessary or forced to. And this is basically the same in HIP, so it looks a little bit differently the main thing. Okay, that's basically what I wanted to say about GPU programming. Yeah, as I said, for one thing, it's basically so complicated, it's yet another lecture. Secondly, we don't have them here in Fukaku, at least not for now. Fukaku next will have them. So in 3 years or so, we have to change the class. And also tomorrow, Professor Vetter, who is a GPU expert from Oak Ridge, he will tell a little bit more about GPU programming in tomorrow. Because we have many people here use Python, I thought I'd show you 5 minutes about some ideas, like when you think about high-performance computing in Python, what you should think about. Perhaps you know already. The problem is, Python is an interpreted language, so it's not compiled, and so typically it's much slower when running the same C program. But meanwhile, there's lots of little tricks you can do to make your Python run, especially for numerical calculations, run as fast as C. Yeah? And then, so here's an example about pi calculation. It's a little bit like the example we used for this polynomial maximum. So it's also basically reading some data, then there's this one loop, try to calculate the digits of pi to some precision, and then it prints it out. This is the the same thing in Python, a little bit simpler. Yeah, you read in the data, you do this calculation, and you print it out. Yeah, so this is one version. Let me quickly go over that. No, so okay. So, and I have the C version. I have a simple version in Python I was showing you. And then I have two other versions I still have to show you. One is using NumPy, and the other is calling. So you see, if the C version, if I run it, takes 0.1 second, 0.12 seconds. If I'm using the normal version of Pi, as you're using as a normal, like just using Python, it runs 20 seconds. So it's, let's see, I'm bad in calculation. So that's 200 times slower, is that right? Yeah, yeah. And so, but you're using NumPy, which basically allows you to work on vectors. And instead of doing one calculation, it does the addition of all vectors at once. Yeah, you can get it down to 7, so it's 3 times faster. And if you're using something called number, you get it down to 0.9. So it's only a little bit slower, but not too much. Yeah, but it's not like 200 times, but say like only 4 or 5 times. Yeah, so how does this look like? So that's the normal calculation. And then basically for NumPy, you basically say import NumPy, and then basically, instead of basically saying, here I do an add and multiply, and here I do some reduction with plus equal, and you loop through it, you basically express it as vector operations. And the first one is like an arrange. Yeah, you take a vector, in each element of a vector, you add 0.5 and divide the whole thing by n. And then here you take the sum and divide by n. So you basically, everything which is a loop in normal Python, you make it basically as a statement, what the loop is calculating on a vector level. And you have to know how to write it in NumPy, this vector expression, but then it can use vector operations in the processor to make it quickly. And then the next step is, the other option is you keep the old version, but you use from number import chit and p-range, and then basically you say, this is a parallel loop by doing p-range, and then chit means just-in-time compiler. So what it does, it takes the Python code, translates it into machine code, which takes a little while, but then basically this machine code is as fast as C code. So it does what you normally, with compiling, with C programs you do before executing, it does basically as the first step very quickly inside the program. Yeah, and with that, basically, as I said, it's still a little bit slower because the time here, which is slower, is the time it needs to do the quick calculation inside the program. So this is just a small example. So if you have a larger program, the time to do the calculation is not just a little. Then it will be getting closer and closer to the C version. So the message I want to just take you, yeah, high performance computer, like thinking like Fukak or something, is perfectly fine. If you do numerical calculations with Python, just learn about NumPy and number, because then the people of a compute center will be much happier because your Python code is very fast. Yeah? Or if you using kind of AI programs where you use kind of TensorFlow and stuff like that, this is internally optimized, also run very slow. It's just if you're writing your own Python. Okay. And here I wrote down some links to either classes with materials or other stuff you can check out. Yeah, so this is a class how to do high performance computing from my labs. Here's all the slides and examples. Here someone wrote an introduction how to use MPI for Python or Python for MPI. Here's CERN is maintaining a list of packages which might be useful for doing Python with HPC. So it doesn't just show things for NumPy and NumPy, but has other things. And then this is what I'm saying. There's an experimental version which allows you to use OpenMP for Python code, and you find here. Okay, one little final word about correctness. Because currently I only told you, yeah, like here's a calculation and how to do it in a parallel program. And I told you, yeah, it takes a while. You can rewrite the code in a way, but it's really fast. Yeah, because it's a high-performance computer, it costs a lot of money. You want to do it very, very quickly. But, yeah, of course you want to do it as quickly as possible, but it still should correct, produce the right results. Sometimes you optimize, and it's much, much faster, but basically it's wrong. And it's not helpful, yeah, of course. So the thing is always make sure your program is correct, and then only then start to slowly make it fast and optimize. And every time check whether it's still doing the right stuff. So there's this famous quote, nobody cares how fast you can compute the wrong answer. Yeah? Only, yeah, you want to basically, everyone wants to know how fast you can compute the right answer. So, which means if I don't know, like the program is wrong, how can I find out what's going wrong? So in programming classes, you typically gets told how to use a debugger. You run your program under the control of a debugger, yeah, a program which helps you locating bugs. And you can step through, look at variables, and see when it's going something wrong. What can you do? Because now you have not one thing executing, you have multiple things executing. How can you debug a parallel program? Guess what? Quite complicated. Okay, so why is it so complicated? So you have all the bugs you have on a normal computer. Of course, yeah, everything you can do it. But now you have it running, you're producing bugs on all processors at the same time. You're producing the same bugs in some cases 10,000 way. So it's a huge amount of things you have to look after and a huge amount of data which can go wrong. Then you have additional bugs which just come from the parallelization and the synchronization and communication, which you don't have in a normal program. And they can be really bad. So, like deadlocks. So the thing is, like you're sending messages, yeah, and say like everyone wants to have something from your neighbors, or everyone is sending to the next group, yeah, at the same time, yeah. 0 sends to 1, 1 sends to 2, and the last one. So everyone is sending, and when everyone is receiving, but because everyone is like, so it could be that everyone is waiting, but because no one is sending, everyone is waiting, and you're kind of stuck. Yeah, everyone is waiting for a message, but no one sends the message before that, and so you're kind of stuck. So it's called a deadlock. Everyone is kind of dead, stopped. I already said race conditions, and this is part of non-deterministic behavior, because now things happening at the same time, it's unclear if there's things happening on two processors which depend on each other, who one is first. Yeah, so someone is writing a value into shared memory, the other one is reading it. It only works if the second process is a little bit slower and reads it after the second one is doing it. This you normally can only ensure if you do some synchronization to make sure, yeah, I write it, synchronize, and then I read it. But as every time you synchronize, you wait for each other, and waiting means I don't do anything other than waiting. Yeah, so you should minimize the synchronization. But the fun thing is, so you don't do the synchronization, and just you run it the first 10 times, and it works fine because the second processor has more to do, and It just works by accident. But then on another day, the computer is very hot. Or like the second process of a board gets hot. So it runs faster or slower depending what the heat does to the processor. Yeah, or the moon is full and kind of has an influence on the speed on the wires. There's all kind of weird things, yeah? Your birthday, your girlfriend gets a child, it can be anything. And then suddenly it doesn't work anymore, yeah? And so there's either race conditions because one is faster than the other, and then we have something called Heisenbugs. You know, it comes from Heisenberg, I don't know what unschärfe Relation in English is. What is the uncertainty or something? Yeah. So I have cases where I run my program, and it works on 1, 2, 3, 4, 5, 17. And when I ran it on 92 processors, it didn't work. And all other numbers from 1 to 100, it worked. Yeah? Or you have things like you find out a race condition, you want to basically find out where it is, so you add print statements. Yeah, I'm here, I'm here, I'm here, I'm here, just to see where it's happening. And then it suddenly works. Because of extra printing, there's a delays, and it suddenly works, yeah? And so sometimes you add print statements and it works, or sometimes you move something, it doesn't work anymore. And these are called Heisenbugs. It's really fun. Yeah, it's because finding that out is really fun. Luckily, there is debuggers who can handle that and control that. The bad part is they are commercial. You have to buy them. And the larger the computer, you have to buy how many processors you want to support, the more expensive they are. But mostly, basically, like centers like RIKEN and large compute centers, they typically buy a license of these, and these are the package to look after for. Okay. Finish. I talked enough. So, yeah. I know computing is difficult, but as I told you yesterday, your laptop, your smartphone has multiple processors. So if you want to really use the power of your laptop and your smartphone or any other computer, you need to do parallel computing. Or at least find someone who writes a program, yeah, like your video player or your game, which uses parallel computing to use your processor. Yeah, so you need to start thinking parallel, which is different than doing one step after another. This parallel. HPC, I said that multiple times, it says computing, but it says high performance computing. So 2 of the 3 letters is high performance. Yeah? These things, yeah, like my machine at home, the Jupyter first exascale machine, costs 500 million euro. We run it for 5 years. Many people will work it. So if someone is wasting a day or two, half of a machine, it's 10,000s of euros. Yeah? So we will basically be on the back of all our users and check them, do they run efficient programs? Otherwise, we will talk to you. Yeah? So you need to think about that. And it's not that hard. You follow some basic guidelines, but this is a different lecture. Yeah? Like what kind of things to look for. Okay, so what is the situation with parallel programming? The programmer is responsible for the data and work distribution. If it's a shared memory system, like on a shared node, you don't need to think about data distribution, but work distribution, how to split up a work, you have to do anyhow. And then as a distributed memory computer, you also need to think about data, communication, and synchronization work. If you have a computer with multiple nodes, you should basically use MPI. Everyone is using that. If you do it inside a node, like a laptop, a high server node, you can do it with OpenMP. If it has accelerators, you use OpenMP 5, like OpenMP Target, perhaps also OpenACC, and you have any combination, you combine that. Here you still have more options, and we have to see in the future, basically, what is kind of like the standard recommended way. But with OpenMP target, as a beginner, it's not a bad choice. Okay, and then basically, this is really just the start. Yeah? So if I got you interested, you say, oh, this is an interesting thing, I potentially should learn more about it. Check out for classes at your local compute center or local university about parallel programming. Here are some books. It's 3 volumes, like The Science of Computing, Parallel Computing for Science and Engineering, Introduction to Scientific Program. And you can download them for free as a PDF from the internet. It's basically like 3 courses this famous person from Texas Advanced Computing Center are doing, and you can even download the example programs and exercises he's using in his class, and everything is for free. So you just download them. You can also buy a book. I recommend that. This is some good friends from Germany. There's standard books for MPI called Using MPI. You get everything on the standard here, and then there's also a book, Advanced MPI. Same thing, OpenMP. There's a standard book using OpenMP, the OpenMP standard, and then there's another book, Programming Your CPU with OpenMP, which talks about these OpenMP target things. And that's it. So we are through. It was kind of like a really, as I said, programming in 2 hours, parallel programming in 2 hours. The idea is to get you started. You know what MPI means, you know what OpenMP means, what CUDA, OpenACC target means, what processes ranks are, messages, synchronization. And if you, like remember that next year, I consider myself successful. I don't expect that you go home and write like thousands of lines of MPI programs. You need extra training for that. You cannot do that. Or you have to be a really good student and just by reading some extra books or something to do it yourself. Yeah? Okay. Some 1 or 2 quick questions. But I think everyone wants to get started now really to work on Fukaku. Okay? Okay then, thank you. So this concludes the programming class.